right, 8th graders, obviously you've noticed I'm gone again today because of my surgery yesterday. So I just wanted to make you guys this little video to go through all of today's assignments. So I'm going to walk you guys through 3.3 thermal energy. And I'm going to have Miss Patton pause as I move through it for you guys to work just like I was here in class. And then you guys will have a little break after you finish 3.3 up. And then you guys will move on and finish up part 2 of the thermal energy review. Okay, so we're going to go ahead and start off with 3.3. But first of all, I just want to reiterate those expectations that I went over with you guys yesterday in class. So hopefully today you guys came in quietly. Okay, you need to make a habit of this as starting next week. Should have been this week, but as far as next week goes, I'm going to have kids online at the same time you guys are coming into class. So I need you guys to be 100% quiet. Sit down, wipe your desk down, sit down, and then do the bell ringer on the board. And the bell ringer on the board should take you guys about 5 to 7 minutes, which allows me enough time to get my DLI kids going. Okay, so you guys should have done the warm-up for 3.3 in your bell ringer for today. So I'm just going to buzz through the first 3 slides of this really quick, and then I'm going to move on to your guys' little mini lab that you guys will be doing in class today. All right, so when you guys came in today, you guys should have opened up 3.3, read the learning target. I can relate the amount of thermal energy of an object to how much energy it has to transfer in a system. So yesterday we introduced this new concept of thermal energy, okay? Thermal energy is the total amount of kinetic energy in the system. So if I give you guys a little picture with 9 molecules in it, and each molecule has a number in it telling you how much kinetic energy each of those molecules had, to find the thermal energy or the total kinetic energy, you would add all them up, okay? This is different than temperature because temperature was the average amount of kinetic energy for that sample. So if we added them up and then divided by 9, which is the number of molecules you had, that would be your guys' average or your temperature. Okay, so I just kind of wanted to review those points for you guys, that thermal energy is the total kinetic energy of a sample, and your temperature is your average kinetic energy of that sample. Okay, so moving on, your guys' warm-up looked like this. You guys should have had System X, which had a cup X with 100 milliliters of hot water, and then that was submerged in container X, which had 100 milliliters of cold water. Okay, then we had System Y, which was set up basically the same, except instead of 100 milliliters of hot water in the cup, we had 3 times as much. You guys had 300 milliliters of hot water in the cup, and then 100 milliliters of cold water in container Y. Okay, we're gonna come back to this image a lot throughout this lesson. So your warm-up, the part you guys actually had to answer on that is you guys had these 3 statements, and you guys should have circled either agree or disagree to say whether you guys agreed or disagreed with each of these 3 statements. Okay, if you guys did not do that, you will need to find time on your own, either in class today without disrupting the process of class, or at home, okay? But that needs to be done right away when you guys come in, okay? So first things first, you guys need to get that warm-up done. All right. Let's move on to the demo. So for this demo in class today, Miss Patton is going to set this up for you guys. And then you guys as students are going to be collecting data and recording it on the sideboard. So everyone go ahead really quick and take a look over on the right-hand side board. You guys will notice this data table that looks very similar to one on the board right now. Okay, so you guys will each be recording times for these samples, and then at each 5-minute time interval, you guys will be taking the temperature of cup X, container X, cup Y, container Y. Basically, we are setting up this demo to look exactly like your warm-up, okay? All right, so at this point, Miss Patton, I'm gonna have you go ahead and set up the demo. The first thing I want you to do is measure out 100 milliliters of cold water and dump that in container X, and then measure out another 100 milliliters of cold water, dump that in container Y. And then I want you to take the temperature and record it on the sideboard so every student can see. Okay, so go ahead and pause right now and measure out your cold water for container X and Y and take the temperature. All right, so everyone, you guys notice that Miss Patton just wrote the temperature in for container X and container Y, which were our 2 cold water samples. You guys need to record those here in a second in slide 4. You don't need to do it right now. Keep your guys' computers turned towards the front of the classroom while you guys wait for more directions. Okay, now Miss Patton, I'm gonna have you measure out 100 milliliters of hot water and pour that into cup X, and then do 300 milliliters of hot water and pour that into cup Y. And then take the temperature of both of those 2 samples and again record it on the side door, or board. So go ahead and pause now to do that. All right, so now you guys should have the information for your initial time for cup X, container X, cup Y, and container Y. Okay, so go ahead, take a second, Ms. Patton, you can pause this video, let everyone record this first line of data into their data table on slide 4. And then when you guys have that, go ahead and flip your computers back towards the front and I'll explain the next part. All right, now that you guys have recorded your initial data, Ms. Patton, what you're gonna go ahead and do is you're gonna open up the timer I sent you. You're gonna use the countdown timer full screen, and you are gonna set this for 5 minutes, okay? When you pick up and then you're gonna pick up cup X and cup Y, and you are gonna place them in each of their respective containers, then you can start the timer, okay? For 4th period, Malaya and Skylar, you guys are gonna be responsible every 5 minutes to come up here and take the temperature of cup X and container X, cup Y and container Y. So one of you guys take the temperature and the other one of you guys is gonna record it on the board, and then you guys will switch at 10 minutes, 15, 20, 25, and 30 minutes until you guys have this full data table filled out. So the timer should be running right now for your guys' demo for this, okay? Those of you guys sitting in class, you guys have either 2 options to record your data. So obviously you'll need to make sure this whole data table is filled out. You guys can either wait until the demo is done and all the information is on the sideboard to record it into slide 4, or you guys can do it as you go, okay? So that little bell ringer is going to kind of interrupt you guys as you go. So Miss Patton, as you hear that bell ringing in the background, you can pause this video to let the kids get their temperature, or if they're good keeping it on their own, you can. All right, 6th period. I'm gonna pause this video right now and I'm gonna have Miss Patton let you guys know who is going to be taking the temperatures at each of the times. So you guys will be assigned a time, and then you guys will be either assigned system X or system Y, where you guys will take the temperature of cup Y and container Y. When you guys are taking the temperature, be really careful not to let the thermometer touch the sides of the container or the bottom. So you don't want to just set it in there and let it get the temperature, because you might be up against the hot cup or the cold water. Whatever the case, you guys want it right in the middle of that water, not touching anything but the water. Okay, so keep that in mind 6th period when you guys are taking the temperature. Okay, so Miss Patton, go ahead and pause right now. Let everyone know what time they are responsible for and the temperature of which system they will be getting and recording on the board. All right, now you guys should all know what time you guys are going to be taking the temperature at, and then whether you're doing cup X, container X, or cup Y, container Y. Remember, you guys are responsible after you get your temperature to go over to the sideboard and record it on the board so everyone can get that data. And again, you guys can either wait till the end where the whole data table is filled out to type your data in, or you guys can do it as you go. That's fine. All right, so let's move on to part 3. On part 3, you guys are going to be building this same demo in the simulation. So not only will you guys be collecting the data in real life, but you guys will be doing it in the sim as well. You're going to see similar patterns, but our water's starting out a lot hotter than their water is, so you're not going to see the exact same data. Okay, and we're not necessarily going to be 5 minutes on the money every time either. Okay? All right, so here are your directions. In the first one, you guys are testing system X. So system X was 100 milliliters of hot water in the cup and 100 milliliters of cold water in the container, okay? Obviously, in the sim, you can't put one object inside of the other. So instead, you guys are gonna just push the 2 objects apart. So let's go ahead and see what this is gonna look like. So in the sim, here's your guys' sim link right here. You guys can right-click, open your sim link, and here's your sim right here, okay? So add a medium sample This is going to be sample A to represent the water in container X. So that's going to be our cold water in the container. And we're going to cool that down to 4.5 degrees Celsius. So here's my medium sample. We're going to cool it down to 4.5. One thing you guys want to do is add your toggles here so you guys can see both the kinetic energy and the energy transfer. So cooling this down to 4.5. All right, now our temperature is at 4.5. You guys can note our thermal energy as well. We'll come back to this number here in a second. Okay, then we want to get the same volume. So if you guys remember, we used 100 milliliters of hot and 100 milliliters of cold. So you guys are going to want another medium-sized sample because we have the same size volume. We want to use the same size samples. So add another medium sample. This will be sample B to represent the water in cup X. So that's going to be our hot water in the cup. And then heat this up to 38.6. So here's our second sample. It's going to be medium, the same size as our cold. And we're going to heat it up to 38.6. Okay, so now our temperature is 38.6. So because we have this view energy transfer toggle clicked, when we push these two samples together in a second, not yet, we still have some more data to collect, you guys will see an arrow showing which way the energy is going to transfer. When that arrow disappears, that's going to indicate that our system is at equilibrium. And I'll talk to you guys about that here in a second. But first, let's collect a little bit more initial data before we push the two samples together. All right, so on slide 6, you guys will see this data table. Note that I've already put in your guys' temperatures for your sample A and B. This is what you cooled sample A down to. This is what you heated sample B up to. Now we need to record their starting thermal energy. So if you guys look right here, sample A has a thermal energy of 15, and sample B has a thermal energy of 90. Okay, remember that's the total kinetic energy. So 15 here, 90 here, and then we need the starting thermal energy of the system. So basically the very instant we push A and B together, we've made a system, and before it starts transferring energy, what's the total energy of the system? So in order to figure that out, we're going to read this little note right here that says, add the starting thermal energy for sample A and B to find the starting thermal energy for the system. So here's A is 15, B is 90, so 15 plus 90 is 105. So the very second we push those together, that whole system has a thermal energy of 105. Okay, now you guys will go ahead and push them together, and I'm only going to show you this for a second. I'm not going to leave them together long enough to let them reach equilibrium, but one thing you guys might want to do first is increase your speed of how fast it is going to reach equilibrium. Okay, this will just mean you guys are staring at your computer screen a little less as far as the time frame goes. All right, so we'll move them together, and you guys will see this yellow arrow represents the energy transferring from this object to this object. And then you guys can see the temperatures and the thermal energies changing. Remember, when that yellow arrow disappears, it's now at equilibrium. And what does that mean? Okay, equilibrium, again, is where you guys have the two samples. They're now the same temperature. Okay, they also have the same average kinetic energy, and they should no longer be transferring energy back and forth. So that's why that yellow energy arrow disappears, is because there's no longer energy being transferred. Okay, so go ahead after you guys have pushed those together and they've reached equilibrium and that yellow arrow disappears, go ahead and record your final thermal energy and your final temperature. Okay, because it is at equilibrium, you should see that sample A and sample B have the same temperature. So these two right here should be the same number. Okay, thermal energy, not necessarily the case. You guys will see that it's not always going to be the case, but this option might be. Okay, and then again, the final thermal energy for the system, add up this one to this one, and that's going to be your guys' final thermal energy. Okay, moving on, you guys are going to do the exact same thing to test system Y, except when we get our hot sample, it's going to be larger. Okay, so let's go ahead and check out the directions. All right, so for this one, add a medium sample and cool it down to 4.5. You guys have already done that. And then add a large sample. Obviously, you guys are going to have to reset and do this all over. Add a large sample to represent the water in cup Y. Notice that we're using no longer a medium, but a large sample. Okay, that represents the fact that we use 3 times as much hot water in our demo as well. So this is going to represent the water in cup Y, and then warm that up to the same 38.6 degrees Celsius. Okay, again, you guys are going to record your starting temperatures, which are already in there for you. Notice that your thermal energies are going to be different than the last data table on slide 6. Okay, add them up, tell me what the system is, And then go ahead, push those two blocks together, let them reach equilibrium to where that yellow arrow is no longer there. And then you guys will record your ending temperatures and your ending thermal energies. And then don't forget to add up your thermal energy for A and your thermal energy for B to equal your thermal energy for the system. Okay? All right, finally, you guys will answer these 3 questions. In both systems, how did the starting thermal energy compare to the ending thermal energy? So what you're going to want to do is you're going to want to go to slide 6, and you're going to want to look at the starting thermal energy. Oops, sorry. Right here. And you're going to compare that to your final thermal energy of the system. Okay? Then you're going to look at this one and do the same thing. Okay, so how did they compare? All right, and then the next question, question 2, is down here at the bottom. Which system reached a higher equilibrium temperature, system X or system Y? So we're going to be looking at this temperature at equilibrium. So this is our ending temperature at equilibrium. So look at system Y, and then go up to slide 6 and look at system X. Okay, which one of these had a higher temperature at equilibrium? Was it X or was it Y? Okay, you guys are going to circle one of those answers there. And then why do you think that system reached equilibrium at a higher temperature? So give me your explanation there. All right, so Miss Pat, I'm going to have you go ahead and pause this video. You guys are going to work through slide 9. So you guys need to finish slides 5, 6, 7, 8, 9. And all the while, you guys should be recording every 5 minutes in your data table here and on the board. Okay, so I just want to remind you guys of that. Your temperature should be, or your timer should be running this whole time. Okay, so once you guys have finished slide 9, go ahead, flip your computers around, and then we'll move on to part 4. All right, moving on to part 4. Okay, one part of this unit that I didn't share with you guys was kind of the underlining theme of the whole unit. If you guys remember that every one of these Amplify units kind of starts with a corny video with bad actors about like, how do we launch this magnetic spaceship into space and where did the pod go and all this stuff. Okay, this one I thought was kind of silly because a principal of a high school was, or a middle school was asking 2 8th graders to figure out which heating system would be best to put in the school. Okay, basically I didn't show you guys that because I thought it was kind of silly. Like, who would put an 8th grader in charge for this huge maintenance problem for the school, okay, in order to keep kids warm on an 11°C day, which is just above freezing. Okay, so, but you guys are going to apply what you guys learned yesterday and today about thermal energy. Because remember now, our size of our sample does matter now that we are talking about thermal energy and how that relates to energy transfer, okay? So you guys are given 2 proposals right here. Proposal 1 is the water heater system, and proposal 2 is the groundwater system, okay? So with the water heater system, notice that the morning air outside is 11°C. So assuming we don't have a working heater, we can also kind of assume that the air inside the school got pretty close to 11°C if our heater wasn't working, okay? Then we install this new fancy water heater system where we have this small water tank that's constantly moving 39°C water around these little pipes. You guys can kind of see their pathway throughout the school, okay, through all the little classrooms and then through like the ceiling of the school, okay? And because that water is constantly circulating, we can assume that it's staying pretty close to 39°C. What's happening then is we're having an energy transfer between the water in those pipes to the air in the school. So the hotter the hotter water in those pipes is transferring its energy to the air, heating the air up, okay? And because it's losing energy, those pipes are gonna cool down as well. Okay, so that's our first system. Our second system is this groundwater. So notice that our tank is a whole lot bigger, but our water's only 30°C. So we have a bigger tank, but cooler water. And again, that groundwater tank is again gonna push water throughout this whole school. So you can see it going again through all the classrooms and up through the edges of the school, okay? And it's gonna be constantly moving, but again, cooler water, larger tank, warmer water, smaller tank, okay? So you guys are gonna be using the sim to figure out which one of these is gonna heat the school better. Okay, there's no data for you guys to collect, but you guys are still gonna kind of mentally need to jot down some temperatures in your head so you guys have an idea of which heater system is gonna work the best. So your test 1 is going to be your water heater system. Okay, so let me pull up the sim here for you guys. I'm gonna restart it and I'm gonna show you guys just the water heater system, and then I'll let you guys do the groundwater system on your own. Okay, so in the thermal energy sim, add a large sample to represent the air inside of the school. Cool this sample to 11.4. So our air in the inside of the school, that's a lot of air, and we're gonna assume it's about as cold as it was outside. So large sample, and again, we're gonna cool it to 11.4. So that's pretty close to the outside air temperature. So there we are at 11.4. Then we're gonna add this small water heater. So it says add a small sample to represent the water in the water heater and warm this up to 38.6. So here's our second sample. It's gonna be small to represent that smaller water heater. And we're gonna warm it up to 38.6. So that's pretty close to 39, which is what they predicted the water in that sample to be. Okay? And then you guys can just kind of take an observation. All right, here's my thermal energy. Ironically, even though this is much warmer than this one, they have the same thermal energy. Okay? And then as far as temperature goes, this one's obviously our cool. Our air is what needs to be warmed up. It needs to have some energy transferred to it. And here's our hot water in our tank. Okay, so same thermal energy, even though, again, this one's hotter than this one. This one's larger. Okay, remember it's total that matters. All right, so we're gonna push those two together. You guys will notice the energy transfer. Remember, when that yellow arrow goes away, that's when the energy is transferred. And you guys should note that these two now have the same temperature. Okay, so the water inside the pipes and the water inside the, or the air inside the school are going to be the same temperature at equilibrium. Okay, so pay attention to what that temperature is. If it helps you guys can kind of jot a number down on here for test 1. And now we're gonna go ahead and test our groundwater system. So because our sample or our water heater is larger, we're gonna do a large sample for that water heater. Okay, so same thing. You guys are gonna add a large sample to represent the cold air in the school. So that's gonna be at 11.4. Okay, and then you're gonna do a large sample to represent the groundwater, but we're only gonna heat that up to 29.5. So that's pretty close to our temperature of 30. So 29.5, so just click it once. So now you guys can see we have a different thermal energy to start versus the last one we had the same thermal energy. Same thing here, you guys are gonna push them together. When the yellow arrow goes away, you guys are gonna now be at equilibrium. You should have the same temperature. So what is that temperature compared to what you guys jotted down for test 1? Okay, and then you guys can move on and answer these two questions. Based on your findings in the sim, which system will warm the school more during the winter? And why will heating this system warm the school more? So explain the why right there, okay? Again, revert back to that concept about temperature and thermal energy. How are they different? How does thermal energy and total kinetic energy play into this? Okay, with the size versus the temperature of those water heaters. All right, finally, I'm not gonna have you guys pause and do that just yet. I'm gonna go ahead and explain the rest of the assignments for you guys so you can get it all done and then have a little break. All right, so after you finish up slide 12, you guys are gonna move on to your reading. So show of hands really quick. How many of you guys have eaten dumplings or pot stickers at a restaurant before? Generally like a Chinese food restaurant or maybe even Japanese. Okay. Raise your hand if you guys like them steamed or boiled where they're more gooey, squishy on the outside. Okay. How many of you guys like them fried in oil so they're crispier on the outside? All right, so this article you guys are gonna read talks about 2 different methods of cooking dumplings. So oil or water. So if you guys are cooking them in 2 different substances that are similar in temperature, why do they have a different taste to them? Why is one crispy and one squishy? Those kinds of things. So these are the 2 questions that you guys are looking for while you read. What are 2 reasons why dumplings cook faster in oil than in water? You guys will get your appetizer faster if you guys cooked them in oil. And what is something new you learned about temperature and thermal energy from reading this article? Okay, once you guys finish the reading, at this point you guys should have all of your data written over here on your guys' sideboard, and all of it should be written into slide 4 as well. So you guys should have this whole data table filled out. Okay, if you guys haven't done so, do so now. And I want you guys to refer back to the data you guys collected here, and also what you guys did in your sim on part 3, okay, with these 2 little data tables, okay? And I want you guys to revisit your warm-up on slide 14. So these were the 3 statements that you guys either agreed or disagreed with in the warm-up. So do you guys agree or disagree with them now? So use your draw tool to circle either agree or disagree. And then when you're done with that, you guys will finish up your wrap-up. Okay, so any questions, yes or no? How do you think you did? 4, 3, 2, 1. And then once you guys are completely done with this assignment, you may hand it in and take a little break. So Miss Patton, if you can go ahead, explain to them what they can do on their break, how long it's going to last, and what time we're going to reconvene to work on our next part. Go ahead and pause now and do so. All right, so you guys just had a good little break. Now I'm going to move you guys on to talking about the other part of your review. And I'm going to be fairly quick about this, but I just want to explain a couple things to you. Okay, yesterday you guys should have completed part 1. If you guys have not done that, it was homework. Okay, so you need to go home and do that. Today you are working on part 2. You guys have a couple different options for how you guys complete slides 9, 10, 11, 12, 13, and 14. I'm going to do 11 and 12 for you guys. Okay, so you guys will need to go back and do 9 and 10, and then you'll need to finish up 11 and 12. I'm not going to do the whole thing for you guys, and then you guys can move on and do the rest of this review. Okay, so first and foremost, what you guys will see in these examples is you guys are going to have 2 samples, and it's going to tell you about each of those samples. Okay, so on slide 11, it says sample C contains 2 molecules, each with an average kinetic energy of 1 kilojoule. Sample D contains 8 molecules, each with an average kinetic energy of 6 kilojoules. Really, guys, the biggest thing I wanted to explain to you guys is this is going to be really hard for you guys to do these problems if you can't visualize them. So up front, I have a little black rack of paper. You guys can either grab a sheet of scratch paper to draw these examples out, or over on the sideboard next to where you guys have like the breakfast food, you guys will see marker boards and markers. You guys can grab a marker board and marker. And if you guys don't want to draw your little kinetic energy in with markers, on the back counter underneath the minion, you guys can grab a cup of those little yellow cubes if you'd rather count them out and use them that way. So you guys have a couple options, but I'm going to show you guys another option as well. So I'm going to go ahead and right click slide 11, and I'm going to go duplicate slide. Okay, so now I have 2 identical slides, sample C, sample C. I'm going to get rid of all the text on one of these. Don't forget to duplicate it, you guys. If you get rid of all the text, you've just erased a big chunk of your guys' part 2 review. So make sure you right click to duplicate it, and then once you know you have 2 copies of that same slide, then you guys can erase the information on one. So I'm going to use the draw tool on this to kind of show you guys how to do this example. All right, so sample C contains 2 molecules, each with an average kinetic energy of 1 kilojoule. So I'm going to have sample C right here. I'm going to draw my 2 molecules. And then, oh wow, that's a crazy molecule. And then I'm going to do some little dots in here to represent my 1 kilojoule of average kinetic energy. That means each molecule has 1 kilojoule of energy. Okay? Going back up to my question, sample D contains 8 molecules, each with an average kinetic energy of 6 kilojoules. So I'm going to go back to my picture. I'm going to draw my 8. 1, 2, 3, 4. I know they're a little bit smaller. 5, 6, 7, 8. It really doesn't matter if they're the same size or not. Okay, and then each of those had 6 kilojoules of energy. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so once you guys have that done, then you guys will take a look. This is going to be my sample D. All right, here's my sample C, here's my sample D. Let's go ahead and take a look at the questions on slide 11. Okay, so which sample would have a lower temperature, sample C or sample D? Look at your guys' image. Which one of those is represented by the one with the lower temperature? Okay, you guys will either circle sample C or sample D, or secret option number 3, they're the same. If you guys decide that they are the same, just write same right over top of your answer. Okay? Which sample where are the molecules moving the slowest? Again, you're either going to circle sample C or sample D, or if they're the same, you guys would just go ahead and write the same right there. Okay, if we only look at one molecule of sample C, what would be its kinetic energy? So let's take a look. One molecule of sample C has one little dot in it, so that would be 1 kilojoule. Same with the next question. If you guys look at one molecule of sample D, what's its kinetic energy? It has 6 little dots in it, so 6 kilojoules. Okay, so 1 and 6 here. And then what would be the final thermal energy of sample C? So remember, thermal energy is your total. So you guys would go ahead and add up all the kinetic energy in sample C. So we got 1, 2. So whopping 2 for the thermal energy there. And then what would be the final thermal energy of sample D? You guys would go, all right, I have 8 molecules. Each of them has 6. So 6 times 8. So we got 6, 12, 18, 24, 30, 36, 42, 48. So my total kinetic energy there would be 48. Okay, you guys can, of course, type those in instead of using the draw tool. Okay, so that's that first part of the slide. The second part of that is going to be doing an energy transfer. So we're going to assume that we push C and D together, and energy is allowed to transfer between the two. Let me get rid of some of my messes out here. Okay, all right. So how you guys can do this is if you click back on your cursor, you guys can click and move your little dots that you already drew. So, all right, you get one, you get one. I would start by just moving one out of the ones who have the most into one of this one, okay? So all of my top molecules here moved into my top molecule of C, okay? And then I'm gonna take one out of each of these as well. And then I'm gonna oops, I took one out of the wrong one. And then I'm gonna kind of reassess how many I have left in each. Okay, so by moving one only from each of these molecules into these 2 molecules, it actually evened it out. We are at equilibrium now. So all of D's molecules, all 8 of them have 5 kilojoules each, and all 2 of C's molecules have 5 kilojoules each as well. Okay, so which way did the energy transfer? You guys notice that I went from D to C. Okay, so you guys would highlight on there, sample D to C. If there's no energy transfer at all because it's already at equilibrium before you move them together, then you guys would do no energy transfer, but that's not the case for this one. Okay, what would be the average kinetic energy of sample C at equilibrium? So that's after you finish moving all of those so they're all even. So the average kinetic energy is going to be 5. What would be the average kinetic energy of sample D? 5. Again, when we're at equilibrium, this should be the same. It's not necessarily the case for the thermal energy. Okay, and then if we look here, all right, the final thermal energy of C, we've got 5, 10. And the final for D would be 5, 10, 15, 20, 25, 30, 35, 40. So your answer here would be 40. So notice that, yes, our average thermal energy is the same, or our average kinetic energy is the same at equilibrium, but not for our thermal energy. These two are not the same, okay? All right, so you guys need to do, I'm going to go ahead and just delete this. You guys can delete it when you're done, too. I don't really care. I just did slides 11 and 12 for you guys. Oh, good. My computer just froze up. You guys are going to do, obviously, slides 9 and 10. Same example you guys are doing. And then you guys are going to move on and do the rest of this. So I'm just going to go through that really quick. Okay, so this one you guys are looking at sample X and Z, and then moving X and Z together. And then moving on, we have which way does energy transfer in a system, what is equilibrium, and what is heat. If you guys need to, refer back to those YouTube videos from the thermal energies demo that we did. There's an actual assignment in your guys' team's assignment. If you need those videos, you can look them up. Okay, same, you guys can use your videos to help you answer the next 2 questions. So this should look familiar to you guys. We've seen this in a video. A metal hard drive and a book are left out in the sun for 3 hours on a 100-degree Fahrenheit summer day. So true or false, circle one of those. The drive and the book are the same temperature. And then when you place your hand on the hard drive or the book, describe which way energy is moving and why. To the touch, which feels hotter. And then why does this feel hotter although they've been in the same conditions for the last 3 hours? Okay, and same condition, or same setup here, except we're at 0 degrees Celsius freezer, so we're going to see energy transferring in different directions here. Then finally finish your guys' wrap up. Make sure you guys have finished part 1. And then when you're done, you guys can go ahead and turn it in. Make sure you guys have checked each and every slide on this, though, before you guys turn it in, okay? All right. So I hope you guys are having a good weekend. And again, I'll see you guys next Thursday, Friday.